please write something in the chat to make sure I can see that happening. Okay, hello, thank you. Thank you very much. All right. Okay, so what I'm going to do is I'm going to go ahead and start sharing my iPad. And so we can continue on with what we were talking about on Monday. So we should be continuing on with our chapter 1, and we're going to continue on with resonance structures in particular. Okay, I did find out one thing about when we were doing our Lewis dot structures. Turns out the Lewis dot structure for our nitrate, which was giving us so much trouble, actually is incorrect. It had 10 electrons around oxygen. That's why the numbers were coming out a little weird. So what I've done is the one I replaced it with in the video online, I'm going to replace it again with a corrected version of the nitrate. So that was what was happening here. We ended up with a total of 10 electrons around oxygen, which gave it a funny charge. And so the other calculations we did were correct, where we were looking at the valence electrons minus 1/2 of the shared electrons minus 1/2 of the unshared electrons or lone pairs were correct. But I just wanted to show you that. And if we go in a couple days to the video, it'll be corrected on YouTube. So it'll have that correct version. Okay. And so I hope you have found where the homework is in the book and have started doing that. Again, you just have to do it sometime before you take the quiz. The quiz can be taken anytime today between 11 a.m. and 11 p.m. So when you go online, make sure you use the test quiz first to make sure everything's working. It looked like about 70 or 80 people had already used the test quiz, so I think most people are working with it. I've had to play with a couple of people in restarting the app, restarting your web browser first and only opening Canvas. It usually fixes all the problems you have with Proctorio not giving you or not letting you get in or giving you an access code. You should not require an access code. It should automatically kick you over. If it doesn't, go ahead and close your web browser, open it back up, and just open Canvas, and that should solve the problem. All right, any questions about the quiz that you're going to be taking before 11 p.m. tonight? Okay. Nobody's furiously typing in the chat there, so I can move on to resonance structures. Can we use scratch paper? Yes, if you show the scratch paper to the screen and then when you're done. That's the only requirement I use for scratch paper. Everything up to resonance theory in chapter 1 will be on the quiz today. Okay, and then the quiz next time I'll have resonance theory on it because we're going to do it today. Okay, so any more questions about the quiz? We should get most of the way through chapter 1 today. We might even start chapter 2 today. I've uploaded a preliminary version of those slides just in case. Yes, it's all multiple choice, just as was the test quiz, so that I'm trying to get you familiar to that format. All right, so what we're going to do is we're going to talk about resonance theory and what happens when there will be a periodic table on the quiz. There's both one in the instructions and in the first question, so you should have a periodic table that you use the one that's in the quiz, don't use any other one. Okay. All right. Any other quiz questions? Will the quiz be composed of everything we've learned up until the end of class today? No, it'll be up until the end of class last time on Monday. So all the resonance theory will be on our next quiz, not this quiz. All right. Okay. So let's say we're drawing our resonance structure and we put our thing with the most bonds in the middle and we start drawing it out and we figured out that, hey, we can draw more than one valid Lewis dot structure. Okay, so what does that mean? That means that we satisfy the octet rule on those that do follow the octet rule. We have 2 electrons next to a hydrogen, and we have up to 10 or 12 electrons up next to a sulfur or phosphorus, okay? But we can draw those electrons in multiple places. Now think about it when we had, so that, what does that mean? Does that mean that one's correct and one's not correct? No, what it means is that maybe just by moving electrons around, those can all be valid Lewis dot structures. And if they're all Lewis valid dot structures, then they're moving the charge from one place, or they're moving electrons from one place to another. And when they're moving around like that, we call that resonance. So resonance is when you have two or more equivalent Lewis dot structures that represent the exact same model, only moving electrons. All right, so let's do that again. So let's look at that as we can draw this carbonate ion here. And we see that we can, you know, when we first draw it here, first of all, let's make sure it's a valid Lewis dot structure. We have a total of 8 electrons around this carbon. Remember, each of those bonds is 2 electrons. So that's 8 electrons around that carbon. And if we look at each oxygen, there's 8 electrons around that oxygen, 8 electrons around that oxygen, and 8 electrons around that oxygen. So that means we have a true valid dot structure, and we can actually look at our formal charge, and our formal charge is going to be a negative charge on this one, a negative charge on that one, and a neutral 0 charge on this oxygen and the carbon. Okay, so that being said, why is it only the 2 bottom carbons that have the negative charge? Why can't it be these 2? Or why can't it be these 2? Well, there's no reason it can't. Okay, that means that we must be moving that negative charge. It's not fixed on this oxygen or this oxygen. It can move around to any of those 3 oxygens. Okay, so what does that give us? Well, that means that we can turn one of these structures into another of these structures just by moving electrons. Okay, we're never going to break our single bonds. We're only going to move lone pairs and double bonds. Okay, so we're only going to be lone pairs and double bonds to make it change to the other structure. So let's go look at the structure again. We're going from this structure number 1 to structure number 2. So how are we going to do that? Okay, we're going to move electrons. And when we move 2 electrons, we use an arrow with 2 prongs on it. Notice that there's 2 here. Remember when we looked at homolytic cleavage, it only had 1 prong there. And when we looked at heterolytic cleavage, we had 2 prongs. That means we're moving 2 electrons, okay? So that being said, we have to look at these 2 electrons in this lone pair are moving in to create a double bond. Now, that other double bond has to move somewhere else because we can't have 5 bonds to oxygen. So what happens is these electrons that were in the double bond kick up and become a lone pair. Okay, so now we have our single bonded oxygen is a double bonded oxygen. Our double bonded oxygen is now a single bonded oxygen and a charge. Okay, so all we've done is moved electrons. We've not created any other system there. Okay, we haven't moved any of the bonds. We haven't moved any of the atoms. We've only moved electrons. Now we can do that again, and it becomes number 3 by moving these electrons up to give us a single bond and a charge, and moving this charge down to give us a double bond and a neutral compound. Okay, do we see how all we've done is move electrons? Electrons can be moved from lone pairs or double bonds around the molecule, okay? We do not break single bonds. We do not move atoms. All right, so that being said, we also have to understand that each of those is equal in energy in that particular case because they all have 2 charges, 2 negative charges, 2 negative charges. So they're not in equilibrium between one or the other, okay? They are in resonance, meaning any of them are correct, not that it's stringed one way or another in equilibrium. So in an equilibrium, it's more like acid and base, where some of the acid reacts, some of the base reacts, and so that leaves some acid and base as acid and base and some as the reacted part to make the salt and water. That is in equilibrium because it can shift back and forth. Resonance, on the other hand, is just moving around constantly. It is not in equilibrium. So when we talk about equilibrium, we use this double arrow, meaning it can go in one direction or the other direction. In the case of resonance, we use this double-ended arrow, meaning it could be either one. Both are right. It could be either one. This means it's moving back and forth. The double arrows this way, the two arrows opposite each other, that means it's going back and forth, which is equilibrium. This means it could be either. Either are good choices for your Lewis dot structure. Okay, so do you understand that those are the two different arrows there? Okay, now, are all resonance structures equal? Not necessarily. So let's talk about how to draw these structures here. Okay, so when we're drawing resonance structures, we need to understand that it's just something we use on paper to describe how the molecule reacts. Okay, so if we were to draw this Lewis dot structure only, and it has a positive charge on this carbon, and we mark this carbon as carbon number 1, and we mark this carbon as carbon number 3, would all of the reactions happen on carbon 1? If we did the reaction and we saw half of them reacted on carbon 1 and half of them reacted on carbon 3, then this one Lewis dot structure does not describe the molecule. Okay, so what we have is our resonance arrow here in the middle that tells us that, well, we have the positive charge on carbon number 1, or we have the positive charge on carbon number 3 here. Okay, because it'll react in each of those positions equally. So what does that mean? That means that we are in resonance because either one of those is a valid structure. Neither one explains it completely. So this is just how we look at it in our head to see that it was that way. Now, what does that look like? Well, all we're doing is we're moving these electrons right here over to here to create our double bond. So that double bond, which is a pair of electrons, is moving back and forth to generate those two Lewis dot structures that give us our pair of resonance structures. Okay, do we understand that that's what we mean by this? This is just kind of a way to keep track of where things are.
I have a question.
Yes.
Does the moving of the double bond, how much change does that really apply to the molecule? Like if it's just moving sides?
Well, if they're moving with equal energy, they're going to move back and forth so fast that it's going to be as if it was in both places at the same time. So it could be either way.
Got it.
Okay. Now, if there's a change in charge, like it go from a neutral molecule to having two charges, that's not the same energy. And so there might be a difference. Okay. So let's talk about that. So we have 4 rules for resonance. Number 1, the position of the molecule, of the atoms in the molecular ion do not change in the resonance forms. Atoms don't move. That's what number 1 says. Number 2, only electrons move. Okay. Number 3, sigma bonds, single bonds, that first bond we make does not participate in resonance. There'll always be that single bond. We never break sigma bonds. Okay. The overall charge of the resonance structure should never change. So when we were looking at that carbonate, it was -2, -2, -2. In the case of this cation on that 3-carbon chain, we were looking at a positive charge on one and a positive charge on the other. So charge never changed. So basically only pi bonds and lone pairs will move. Everything else stays the same. All right. So that means that we can write a Lewis dot structure that just has to satisfy all of our possible rules first. We have to prove that we have a valid Lewis dot structure before we move on to writing our resonance structures. So if we look at this structure here, this hydrogen has 2 electrons, this hydrogen has 2 electrons, this hydrogen has 2 electrons. So all the hydrogens are happy. Let's see, this oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. because there's 4 here, 2 here, and 2 here. So oxygen has 8 electrons, but we have a problem. We do not have a valid Lewis dot structure because carbon here has 10 electrons around it and it has 5 bonds, okay? That means this cannot be a valid Lewis dot structure for methanol, okay? So even though it balances out to 0 charge and we have most of the atoms follow our octet rule or hydrogen with 2, it does not follow the octet rule. So it's not a valid structure. So we have to eliminate that from our resonance possible structures. Okay, so let's say we have a valid Lewis dot structure. And in this case, we have right here, we have 8 electrons around this one. We have 8 electrons around this one, and we have 6 electrons around this one, but we have a formal positive charge. Okay, so we have an empty orbital there, but it has a positive charge, which accounts for the fact that it's missing that 1 electron in that bond. So it is a valid Lewis dot structure. Now, we cannot break any carbon-hydrogen bonds, and we can't break any of the single carbon-carbon bonds, the sigma bonds. We can only move the pi bond or the double bond or electrons back and forth. So what we see here is that now this one right here is a Lewis dot structure, valid Lewis dot structure. And by moving these electrons over to here, we now have a second Lewis dot structure that is valid. And that means these 2 Lewis dot structures are in resonance with each other. Okay, see how we didn't move atoms, we only moved electrons, and we had the same charge in both of those systems. And we did not break any sigma bonds, any of those single bonds. All right, questions on that? Okay, so we can write those with negative charges or positive charges or no charges. It all depends on where you're moving the electrons. So an example here, we showed that we have that positive charge moving from the first carbon to the second carbon, I mean to the third carbon over, and it can move back and forth because it only moved those electrons in this double bond right here. So we can also move a lone pair of electrons. In this case, we have a carbon with a negative charge. This lone pair can move in, kicking this double bond out to be a lone pair on the other. Notice we still have the same charge. We haven't broken any carbon or hydrogen bonds, and we haven't broken any carbon-carbon single bonds. We've only moved electrons. So that means it is a valid resonance structure. Okay, so let's dig a little deeper on how to write these. So the first thing we want to do is we want to find a valid Lewis dot structure, okay? And so if we were to write the valid Lewis dot structure for this compound here, we would end up with a neutral molecule because the formal charge on all of the atoms is 0, okay? However, we can actually write a valid Lewis dot structure that looks like this, where we have 8 electrons around here, 6 electrons, but a positive charge. And therefore, technically, this is a possible Lewis dot structure because, well, it has charge, it has the total molecule has a 0 net charge. Okay, now, which is more stable? The one without the charges and with all atoms having an octet is more stable than the one with the separated charges right here. Meaning that if we were to say which of these contributed more to the structure, what does it look like most? It would look most like this. Again, we're not in equilibrium. It's not shifted to that one. It would just look most like this. Okay, so it is the greater contributor. So the one without charges, the one with octets, those are the ones that are more stable, and therefore those are the ones that are a greater contributor to the hybrid. So what does this mean though? Because we have this resonance hybrid here that shows this charge, that means part of the time we have a little bit of positive charge here and a little bit of negative charge here. And we're going to go into that a little bit later about what that means and how that that less stable resonance structure actually contributes to how that compound reacts. Okay. So when we use these resonance structures, we show the flow of electrons using curved arrows. When you move one electron, it's one arrow. When you move two electrons, I'm sorry, one barb on your arrow. When you move two electrons, there's two barbs on your arrow. And notice when we do resonance structures, only electrons move. And we typically move them two at a time. Sometimes we move them one at a time, but most of the time we move them two at a time. Okay. So by using those arrows to show where the electrons flow, we don't break any bonds. We just create lone pairs, and we create or remove lone pairs and create or remove double bonds. So let's look at that a little more in what we are using these curved arrows for. We use these curved arrows all the time to show where the electrons are flowing. So you always have to flow from electrons to the place that has an electron deficient center or that wants electrons. Okay, so that means in this example here, the hydrogen here with the positive charge does not have the electrons. Therefore, we have to use an arrow that goes from the negative charge to the positive charge. We do not go from positive charge to negative because remember the arrow shows electrons moving. Two barbs, two electrons moving. So in the case of here, we have this lone pair that's going to come here and attack this partially positive side of that carbonyl compound. Okay, we showed that it had a partial resonance structure that made it positive there, but that's not the major resonance structure. So it's only partially positive, and therefore the electrons flow to that positive charge. Again, there's no electrons here to flow to these electrons. So this is incorrect way to draw our arrow. We always draw the electrons going to the other part. Now here we have two movements of electrons. We have the electrons from the OH moving to form a new bond with the hydrogen, and the electrons in the bond with the hydrogen forming a negative charge on our other compound here. Notice we have a net negative charge across that entire equation, so it's not bad, but the two sets of electrons had to move to get to this side of the reaction. Okay, do we see that two barbed arrows move electrons from where they are to where they're forming the new bond? Okay, so we can use this in a number of ways, and we're going to use this a lot through both our first half of organic, but we're also going to use it a lot in the second half of organic. So let's think about a couple of the weird structures we have. So in the case of this, we just have single and double bonds between carbons right here. And we can move those electrons to give us see the double bonds in this place, and we can move it over to here by just moving those electrons. And so both of these would be valid resonance structures. In fact, they move around so fast, most of the time, we actually write the structure with the ring in the middle of it, saying that they're just moving around and around and around and around this ring. Okay, not all resonance structures move around rings. Sometimes we have our negative charge from an oxygen come in to give us a double bond here, and the double bond comes up and gives us our negative charge here. So in this one, our negative charge is here. In this one, our negative charge is here. Okay, so if we were to look at what the average of those two resonance structures would be, we would see it would have partial double bond here, a partial double bond here, and the negative charge is going to be spread out over that entire region, that both of those oxygens and a little bit in that carbon. So that negative charge is going to be spread out. Okay, so these are the resonance structures. This is the resonance hybrid. These are the resonance structures. This is the resonant hybrid. Okay, and so if we look at ozone right here, it actually is a dipolar molecule as it sits. We're going to move two electrons in and move the negative charge over here to give us this second valid Lewis dot structure. Okay, now notice we have two charges here. We have a positive and a negative. So in our resonance hybrid, we have a neutral molecule. partial double bond here, partial double bond here, but a net charge of 0. Okay, so that's the value of having 2 correct resonance structures, 2 or more, and showing what the resonance hybrid would look like. Again, that resonance hybrid does not exist. It's just what we use to show us why things react in a certain way. Okay, questions on resonance structures versus resonance hybrid? Okay, so I said that sometimes, even though they're not in equilibrium, sometimes one of the resonance structures contributes more to the hybrid. Okay, it contributes more to the hybrid. So instead of being a perfect circle, like up here in the case of benzene ring, we don't have that perfect symmetry of the system. In this case here, we have a neutral molecule and everything has an octet. So it's more stable, 4 covalent bonds and no charges. In this case here, we have 3 covalent charges, 3 covalent bonds to carbon and 2 charges. So that is less stable than the one with 4 covalent bonds and no charges. Okay, that being said, it's still in resonance, meaning our resonance hybrid has to look not like this and not like this, but somewhere in between, but knowing that this is the more stable one, meaning it contributes more. So the total resonance hybrid would look something like this, where we have a hydrogen here, and then we have these brackets around it showing it's our hybrid. And then we have a partially positive charge on carbon and a partially negative charge on oxygen. So our resonance hybrid looks more like the more stable one, but the less stable one is represented by having those partial charges. We don't have full charges because it's more like this. We have partial charges. Okay, do we understand what that partial charge? That little symbol there is delta. Delta minus is a partial negative charge. Delta plus is a partial positive charge. Okay. Okay, so how do we decide which one's a little more stable? Well, we can use our looking at our electron configuration to see. The more like we are to have our octet, the more the bonds that we have, the more likely it is to be more stable. Okay, if every atom in our structure has an octet, it's going to be more stable than those that don't. Okay, so imagine we're trying to fill our octet again, look like that noble gas structure with a filled orbital, like neon here, and that gives us our structure. All right, questions on resonance and resonance hybrids?
Oh, I have a quick question.
Okay.
So whenever we're looking at the structure and we see that negative on the side, like on slide 64, whenever we see that negative and we see that that's moving and creating another bond, does that mean that there's 2 electrons that we're moving, or is it just a single electron?
2 electrons are moving.
Okay, so having that negative on the outside is relatively the same thing as having like a lone pair of electrons on the outside?
Well, the negative charge is actually because you have 1 electron added to it to give it a lone pair. That lone pair is the thing that kind of moves back and forth. We move pairs of electrons most of the time to form double bonds. Okay.
Got it.
Okay.
Okay, thank you.
But again, look for the double pronged arrow, because sometimes we move 1 electron, and when we move 1 electron, it only has 1 prong on the arrow. So 1 electron is going to be like that. 2 electrons is going to be like that. Always. So that way you can look at the arrow and see how many electrons are moving. Okay.
So if we see a single pronged moving towards like, for example, if it's a single prong and it's moving to make a double bond, then we know immediately that it's incorrect because you would need another electron to form that double bond.
Correct. Or you could do it where you have carbon, double bond, carbon, carbon with a single electron. This single electron will move in, single barb. This single electron will move in, and then this single electron will move up at here to go over here. So you just have to look for a single barb or a double barb. You can actually move a double bond around if you move in a single electron from one side and a single electron from the other side, and it'll give you the single electron here. So again, look for the number of barbs to be sure that you're moving 2 electrons or 1 electron. Okay? All right. So let's talk a little bit about this. Okay, so we have these electron configurations that we have, and we know we have our first energy orbital and our second energy orbital. Okay, and in our second energy orbital, we have 2 different shapes of orbitals. We have a spherical orbital, the round one, and the p ones, which are dumbbell across the x, the y, and the z. So in theory, we have a bunch of different ways that we can bond these things like carbon or nitrogen or oxygen. Okay, so let's talk a little bit about molecular orbitals. Okay, so why do we share electrons to make a covalent bond? Okay, well, the first reason is the difference in electronegativity, right? Neither one is so electronegative that it wants to steal the electron from the other one. So we have that going for us. But the next thing is, okay, so let's see. The outside of an atom is electrons. The outside of an atom is electrons. They are pushing each other away, okay? All right, the inside of the atoms are positively charged. The outside of the atoms are negatively charged, right? But they have to be moving really fast to keep from colliding together. All right, so what we're gonna do is we're gonna take this charged center and this charged center, and by moving 1 electron somewhere in between those 2 nuclei, we can get a certain amount of electronic attraction. There's 1 more electron on this outside of the atom than protons over here, and so they're pulled together, okay? If the center of the nucleus cannot feel the a negative charge of the electron, there's 0 attraction. We're over here at number 1. We're so far away that we don't see any attraction. But let's say they get close enough, and so this nucleus can start to see this electron, and this nucleus can start to see this electron. So what's going to happen is they're going to start to pull together, and at some point they're going to reach equilibrium between it's pulling the extra electron from the one atom and this electron from that atom, but then there's the other electrons that are repulsing each other. So these are attracting, and then the other electrons are repulsing. So there's going to be this equilibrium where the attraction and repulsion kind of is at its minimum energy or at an equilibrium, okay? That is where we have our covalent bond, okay? So then if we try to squeeze the things too close together, we're going to have nuclear, the positive charges are going to start to spread each other apart. You go too far out this way, the negative charges are going to spread them apart. So the actual balance between that shared electron and that nucleus gives us this covalent bond. And in there, we actually have a less energy is required than having them unpaired electrons. They shift down, they form this covalent bond and both electrons are somewhere in between those 2 nuclei, and they have a savings in energy. Savings in energy means that it happens naturally, it's more stable. Questions on this demonstration of why atoms come together to form covalent bonds? Okay, so if we think about that and then we look at how our structure of carbon is, we started filling our ground state here, and then we started into our second state with a total of 4 valence electrons, okay? So when we fill those up, we filled them from the bottom up, right? So we have 2 in the S, 1 in one of the P's, and 1 in one of the P's, okay? So let's say we have 2 electrons here, and we have 1 electron in this orbital, and then 1 electron in this orbital, okay? So how are we going to get 4 bonds there? Well, we can bond twice to this. We can share those 2 electrons in the spherical one, but then we have to share the other two in these p orbitals here. And it's going to be really weirdly shaped. It's not going to be evenly shaped. This is going to be the X, this is going to be the Y, this is going to be the Z, and this has to shoot off at some weird angle. Okay, but we don't see that. We don't see that. When we look at these compounds, we see 4 equivalent lengths of bonds, 4 equivalent, and they're spread out as far as possible. Okay, so what has to happen to go from these 3 different p orbitals right here that are all in that XYZ configuration and these s orbitals that are round and don't have like that lobe shape right here? Well, we have 4 electrons. So what if we took all 4 of those second energy level orbitals, the S's, the S, we have 1 orbital in S and 3 orbitals in P. What if we blended them together so that we have 4 equal orbitals? Okay, so what would that look like? Well, if we did that, what it would look like is, well, we had our 2 S's down here. We had our 3 P's up here. Notice the P's are in higher in energy. So if we give up some of that P and we add a little energy to S, we're going to blend all 4 of those orbitals together to be of equal energy. And that means we can take in carbon, we can take all 4 of our, there's not an electron here, all 4 of our carbon electrons and put them into 4 equivalent orbitals. So what does that mean? Well, if we have 4 equivalent orbitals, that means we can spread them evenly around the atom. So if we looked at methane, what we see is that we have 4 equal bonds and they're all spread out in space as far apart as they can be. Okay. If it was the X, the Y, and the Z, each of those would be 90 degrees apart. But now we just have 4. And it turns out in space, it's 109.5 degrees is as far as you can get 4 different objects in a 3-dimensional space. Okay. So we call that is our tetrahedral structure. Tetra meaning 4, hedral meaning object. So we have tetrahedral structure, and each of those bonds is 109.5 degrees. So if we see that hydrogen looks like this, and if we imagined blending the S's and the P's to give us 4 equal orbitals, that explains why carbon bonds equally 4 times. And it bonds, tries to give those 109 degrees when it has only single bonds. Okay. So what happens in the case of, so here you only have hydrogens and carbon. What if you have 1 more carbon? What really happens here? Well, okay. So we started with this round one in the S. And then we started with a P along the x-axis, a P along the y-axis, and a P along the z-axis. Okay, so that means we have to change the shape of both of them. They're no longer spherical. They're no longer perfect dumbbells. So what we're going to have to do is we're going to have to add some of the S to each of the P's. When we add some of the S to each of the P's, we get a bigger lobe on one side and a smaller lobe on the other. So we have a bigger lobe on one side and a smaller lobe on the other. And so what we see is that they're no longer aligned in the X, Y, and Z axis because they're trying to spread out as far as possible. So if we look at that, we have the big side of each of these orbitals are spread out to give us that 109 degrees. And what you might not see is that there's this little teeny other side of this p orbital, and those actually nestle right in between the different groups that are out here. So that's the other side of the orbital. Okay, so we have a big side that has S and P character. So it's dumbbell, but it has more S in it, dumbbell, but more S in it. And these aren't charges, they're just sides of the orbital. So that's how we get it to go from an S orbital and 3 P orbitals to 3 move it to 4 equal orbitals, and it has both s and p character. So that means we turn the 1s orbital and those 3p orbitals into an sp3 hybrid orbital. So that it has s and it has 3 p's for a total of 4 equivalent orbitals, and we call this sp3 hybridization. Okay, so we're hybridizing the s orbital and the p orbitals in that second energy level to generate 4 equivalent shaped orbitals that are all at 109.5 degrees apart. Okay, so that being said, we've done this hybridization. So when we squeeze these together, another way to look at it is we have this s orbital that's in phase with these, and it's going to split up that s energy and split it into those, giving us the bigger side of each of these lobes. The other side of the orbital is out of phase with the s orbital and it gets smaller. Okay, so when we see that, when we look at a carbon and we just have 4 hydrogens around it, we're going to see there's those oops, let me change color here. We're going to see we have these 4 lobes that are all at 109 degrees apart. Each of them have 1 electron in them. We have hydrogens which only have s orbitals. Each of those has 1 electron in it. So this electron is going to pair up with that electron to make a sigma bond, a single bond. This electron and this electron is going to pair up to make a sigma bond. This electron and this electron, a sigma bond, a sigma bond. So in this case here, we've taken those 4 hybrid orbitals with 1 electron each, shared those with the 4 hydrogens with 1 electron each to make 4 equal orbitals, 4 equal bonds, and we call that single bond, that first bond, a sigma bond. Okay, so we've made 4 sigma bonds. But how do we do it when we have something other than that? Well, we have an idea here that we can, oh, I don't want to use that structure, that we want to bond to this larger axis here. And if we have one that's carbon that's next to the other, we can actually have those hybrid orbitals bond to each other. Okay, so here we have, in this case, we have 4 sp3 hybridized orbitals right now. There's no hydrogens yet. And we have another carbon over here with 4 sp3 orbitals. What can happen is we can then take this 2 hybrid orbitals and make a sigma bond, make a single bond between those 2 carbons. Okay, so this is a carbon-carbon bond right here with an sp3 hybridized orbital bonded to an sp3 hybridized orbital. Okay, now we can fill all of the other 6 orbitals with hydrogens. So we'll have 6 hydrogens, and each of those is going to be an sp3 hybridized orbital from the carbon with the s orbital of the hydrogen. And we're going to make more sigma bonds. Okay, questions about how we're stacking these hybrid orbitals together to make sigma bonds, or those first bond you get between atoms. Okay, so that's when we have 4 equal orbitals when we take the s and all 3 p's and blend them together. Are there other ways of doing this so that we can get different structures? Well, yes, there are. So what if we don't blend the s with all 3 p orbitals? What if we only blend it with 2 of them? Okay, so we had an s and a p and a p and a p right here. And instead of blending all 3 to make an sp3 hybridized orbital, which would give us 4 equal orbitals right here, what if we only did 2 of them and we left this p unhybridized? So that means we're going to have an sp2, and we're going to have a total of 3 orbitals, 1, 2, 3, plus we're going to have an unhybridized p orbital. Okay, so that means all of these sp orbitals are going to be the big lobe, small lobe, sp2, And then we're going to have one orbital that's untouched, the P. It's going to be the PX or the PY or the PZ, whichever it is, it's going to be untouched and have the same size lobes on both sides. Now, if we have 3 equal orbitals, turns out the farthest we can spread 3 equal orbitals out in space is 120 degrees. Okay, so if you see a molecule that has 109.5 degrees, chances are that atom has SP, the central atom has Sp2 hybridization. If you see a molecule that has 120 degree spacing between its bonds, it probably has Sp2 hybridization. And then there's going to be an unhybridized P. That unhybridized P can do different type of bonding. We're going to talk about that next. Okay, so let's talk about how we did this. Okay, so we started with these right here, and we have this. Remember, in carbon, we have 4 valence electrons. So it's in group 4A. So we only have the 4 electrons. So to help spread those out evenly, we can take 2 of the p orbitals and 1 of the s orbitals and get 3 equal orbitals. And these are going to form our sigma bonds. Okay, this p orbital, the p orbital cannot form a sigma bond. The p orbital, only the hybrid orbitals can form sigma bonds, or the s orbitals can form sigma bonds. P orbitals cannot, and they actually form a different kind of bond called a pi bond. And we're going to talk about that in a little bit. Okay, so we've gone from, instead of blending all 4 of these together, we only have 3 of them plus an unhybridized P. So what does that look like? Well, we have the hybrid orbitals here in blue, and they are evenly spaced out in space as far as they can get, which is 120 degrees. Okay, so 120 degrees and 120 degrees and 120 actually leaves a nice triangular shaped plane. Well, that p orbital comes up and out, up above and below that plane. Okay, so that gives us an opportunity. Okay, so in this case here, we're going to take our p orbitals and bond to hydrogens, and then we're going to take, our sp3 orbital, our sp2 orbitals, and bond to the carbons and the hydrogens, and those are going to give us sigma bonds, our hybrid primary overlap sigma bonds, and that gives us our p orbital above and below, and the p orbital on the next carbon above and below. Okay, so what it's going to do is, instead of bonding directly between 2 nuclei, i.e. a sigma bond is directly between the carbon nuclei and the other carbon nuclei, what we're going to do is we're going to do what's called an overlap bond. We're going to bond above and below the plane. Okay, why is it above and below? Well, I mean, we have the shape is equal on both sides, right? Above and below the plane. And there's 1 electron in one of these orbitals, and there's 1 electron in one of these orbitals, right? But that load means that we could have the electron down here too. So the electrons could be down there, or they could be on the top. They spend equal time in both, which means that when they overlap, we can have part of the time the 2 electrons are on the top, part of the time the 2 electrons on the bottom. See how that overlaps, that sigma bond, that direct bond between the nuclei? We call that overlap bond made with p orbitals a pi bond. Okay, now let's look at the drawn structure here of ethylene now. So now we have our 120 degrees between those, 120 degrees between those, and our pi bond goes above it. So anytime you see 2 lines between atoms, the first line is the sigma bond, directly bonded between the 2 nuclei. The second line is always a pi bond, an overlap bond. If you have a third line, that third line is another pi bond. So how do we get it to the third line? How do we get another pi bond? Well, let's see about changing our hybridization structure, right? So instead of going from our ground state where we have just our 2 electrons here and our 3 electrons here, let's go ahead and move it so we have all of our electrons kind of spread out among those orbitals. And then we're going to move the energy such that we get to Our sp2 are 3, which are 120 degrees apart, and then our p orbital here by itself, which creates that overlap. Okay, so what if we don't do 2 of the pi orbitals and let's do 1 of them? Okay, so when we do the 1, these are the same pictures here, interesting. We can change our, oh, we have to do this, sorry. I was trying to go to the sp hybridization, but I'm going to stop here. Okay, so we've hybridized it, so we have 3 equal sp2 orbitals that form sigma bonds. And we have 1 p orbital that forms that double bond. So what does that look like? Well, in a flat structure, we see that it's about 120 degrees apart, okay? But notice it's not exactly 120 degrees. That's because the carbon is larger than the 2 hydrogens here. So it's going to spread it out just a little out of that 120 degrees. And these 2 hydrogens are smaller than the carbon over here. So they're going to be squeezed slightly together. Okay. So our ideal is 120 degrees, but our actual is just a little bit different based on the size of the atom. Okay. So what would just one of these carbons with hybridization look like? Well, we would have our 3 hybrid orbitals are going to be equally distributed at 120 degrees apart in that plane. So they'll make a nice triangular shaped plane here. And our p orbital, which is equal on both sides, is going to be equally above that plane and below that plane. It's going to spend half its time above, half its time below, just go back and forth, okay? So now we see our structure where we can do direct bonding with these orbitals, and then we can use those p orbitals to overlap with other p orbitals to give us our overlap bond or our pi bond. Okay, so this is what that looks like here. So we've got our sigma bonds here. This is our hybrid orbital, and our hybrid orbital, all at 120 degrees apart. They're going to give us our direct overlap between nuclei, which is our sigma bond. Then we had 1 p orbital here. Oops, let me do it. We had 1 p orbital here and 1 p orbital here, and those are overlapping. Those are going to share a total of 2 electrons. Okay, all sigma bonds are 2 electrons. Each pi bond is 2 electrons. So that means if we look at this structure here, how many electrons do we have between these 2 carbons?
4.
4. We have 2 for the first one, which is a sigma bond. We have 2 for the second one, which is the pi bond, a total of 4 electrons. And if we ended up putting a third bond there, we'd have a total of 6 electrons between those 2 carbons. Okay, so each line counts as 2 electrons. All right, so now we have our structure that lets us show how it overlaps to give us a pi bond, and that we have 3 equivalent hybridized orbitals, which means it's sp2. S is 1, p and p, a total of 3 orbitals blending together to give us 3 equal energy orbitals, the sp2 hybridized orbital. All right, so another way to look at that is that, you know, we had that when we looked at this, the orbital is kind of shaped like this and like this, and then we're starting to blend it together, okay? So if we really looked at where the electrons might be, they could be anywhere in this whole donut above or this whole donut below that sigma bond, okay? So the hybridized orbital actually kind of spreads out and can be anywhere in that area. So we think about it here, we have a lot of electrons above and below the plane made by these 6 atoms. All right, questions on that? Okay, so if there's those electrons above and below, and we have to have these p's kind of right next to each other, kind of lined up so that we can share, what does that mean? that means that we can't rotate around a double bond because we'd have to take a p orbital and rotate it out of plane with another p orbital. So because to take this and rotate around this bond right here, we would have to tilt this out of plane. It would be tilted in this direction and in this direction here. We would have to break the pi bond to rotate. So we're not going to break the pi bond to rotate. What we're going to do is we're just going to call that fixed in that system. So in this case here, once we have our pi bond, let's say we had let's call it chlorine here and a chlorine here. Those chlorines are going to stay exactly in that position because there's no free rotation around there. If we just had a compound Cl, Cl with hydrogens here, and we just had a sigma bond, we could rotate it around so that those two chlorines were next to each other. We can't do that with a pi bond. It doesn't let you rotate around the double bond. Okay, so what does that mean? That means we actually have different structures we can make with a double bond where we can have the same group on, or different groups on different sides. So if we have it right at the end of a chain, we're going to have a total of 3 hydrogens, and then this is going to be some kind of carbon. If you're drawing the resonance structure, then you wouldn't break the double bond since it's fixed. Yes, you can't rotate around that double bond in the resonance structure that has the double bond in it. The one that doesn't have the double bond in it, it can rotate. So there's a question in the chat about if you were drawing the resonance structure, then you can't break the double bond since it's fixed. The answer is no. On the resonance structure that you have the double bond, it doesn't rotate. If you move the double bond to a different location, that bond doesn't rotate, but where it was can, as long as there's only a single bond there. Okay. All right. So in this case here, we really can't tell the difference if these two are in the same position or not, because it's actually identical. If we flop to these two, there's no difference between an R group next to a hydrogen and an R group next to a hydrogen. However, if we put the methyl group here and the propyl group here, and we still have 2 hydrogens here, again, it's the same thing. You can't tell the difference between them. Okay. However, if you have 2 groups that are different and you can tell the difference between them on either side, they have isomerization. Basically, isomers are different structural devices. And in this case, because we don't have free rotation, we can have isomers. So if they're both of the groups on a di-substituted double bond are in opposite directions of each other, we call that to be trans isomer. Trans meaning opposite. And if they're on the same side of the double bond as each other, so here's the double bond, they're on opposite sides of that double bond, that's trans. If they're on the same side of the double bond, we call that cis, meaning same side. And that's all because we do not have rotation around that double bond. So we use this predominantly only when we have di-substituted alkenes, okay? When we have tri-substituted alkenes, we're actually going to look at that in chapter 3 about the different nomenclatures for that. But when we have the di-substituted, we can say cis and trans isomer to tell you exactly where something is. So let's say you had a bromochloroethane. So you have 1 bromine and 1 chlorine. Well, you could draw it one way, like this, where they're on the opposite sides of that double bond. Or you can draw it this way, right here. Which one's right? Well, they're both right, assuming, but now because they're on different sides, you have to be very specific about your nomenclature. And in this case, where they're on opposite sides, we call that the trans bromochloroethane. And if they're on the same side, we call that the cis chromochloroethane.
Does that not change the polarity or the electronegativity at all?
It does not change electronegativity because that's the individual atoms. It does change the polarity. And we will talk about that. All right. All right, so we can see that. And if we have more than 3 groups, if we have more than 2 groups, we actually want to use a different nomenclature system. But notice we can use cis and trans quite a bit. In this case here, we have 2 groups, and notice we have 2 hydrogens. The hydrogens are on opposite sides, the 2 groups are on opposite sides, so we call that the trans isomer. If we look at this, both of the alkyl groups are on the same side, so that's the cis isomer. In this case here, the 2 hydrogens, notice the hydrogens here, are on opposite sides, and the 2 other groups are on opposite sides. That means it's the trans isomer. And if we looked at the double bond, both of the groups that aren't hydrogen are on the same side, therefore it's the cis isomer. All right, questions about cis and trans and rotation around that double bond?
So really, we'd only use these when we're talking about like alkenes that are disubstituted.
Disubstituted alkenes, yes. And we're going to hit this again in nomenclature, but I just wanted to introduce the topic that because of that hybridization, we do not have free rotation. Okay?
Okay.
Okay, so now that we have hybridization where we had the S and all 3 P's making 4 equal sigma bonds. And then we had the S, 2 of the P's and made 3 equal hybrid bonds, plus having a p orbital that allowed us to make a pi bond. What happens if we only blended 1 S and 1 P together to create 2 equal orbitals, and then had 2 P's available to do overlap bonding or pi bonding? Well, what that looks like is that gives us a triple bond. Because when we have S and P, where we have 2 equal orbitals, turns out in space, the farthest you can get 2 orbitals away from each other is 180 degrees. Okay, now that's great because that leaves the one of the P's in the x-axis and one of the P's in the y-axis, and our SP is going to be in our z-axis. So our structure is going to turn out to be linear. We're going to have all the bonds that are away from the triple bond being 180 degrees apart from each other. And we're going to have 2 pi bonds, one in the x-axis, one in the y-axis. So what does that look like? Well, we have to change our hybridization state. So we want to get to a total of 4 orbitals because we have 4 electrons. So what we're going to do is we're going to hybridize 2 with one of the P's and the S to give us 2 equal orbitals that are hybrid. And then these are 2 unhybridized P's. So the PX and PY are unhybridized, only the PZ is hybridized. And that gives us a possibility of bonding in a certain way. So when we look at that, we see that this is the hybridized orbital right here. And we're going to call that the z-axis. And then we have the orbital in this direction, which is the x-axis, and then this orbital here, which is the y-axis. Okay, so those 2 p orbitals are spread out as far apart as possible. That sp hybridized orbital is now spread out as far apart as possible. They're each 90 degrees apart. Okay, so when we make a sigma bond, we're going to make our sigma bond with the hybridized orbital. So if we go to bond these 2 together, we're going to bond the hybridized orbital together to make our sigma bond. And then this is our hybridized orbital bonding to the hydrogen. This is our sp bonding to the hydrogen. So all of these are our sigma bonds right here. And then we have a p orbital in the x, right? So this is our p orbital in the x and our p orbital in the x. These 2 are going to overlap each other to make our first pi bond. Then we have our p and our y axis here and our p and our y axis here. They're going to overlap to make our second double bond. Okay, so when we draw it, we see 3 lines. Okay, in our 3 lines here, the first line is always a sigma bond hybridized orbital. The second bond is always a pi bond, an unhybridized p, And the third bond is always a pi bond, an unhybridized P. All right, questions on that? So what does that mean? Well, it actually tells us something a little bit about the strength of the bonds and the length of the bonds. In the case of an sp orbital, you're made up of one s and one p. So that means it's 50% s, 50% p. So imagine it's going to have a very big lobe and a very tiny lobe here, because it's mostly s, it's mostly round. Okay. Now, s orbitals are closer to the center, and therefore they hold their electrons tighter. Now, if we go to our sp2, we're going to have 33% s character. So we're going to have a bigger lobe, but we have 66% p character. So notice the bottom lobe is a little bit bigger and the top lobe isn't as big. Okay. So that means that there is going to be a slightly longer bond than the sp, but it's going to be shorter than the sp3. In the sp3, we only have 25% of it s, because it's spread out over 4 equal orbitals. And so when we look at that, it's going to be closer to that, where we have a oversized side of the lobe. It's round, but it is not as big and round as the sp2, which is not as big and round as the sp. Okay, so we actually see a different size in the lobe of the orbital, and that leads to bonding strength. All right, questions on these different sizes? All right, we have about 12 minutes left, so we're going to talk about bond lengths. Okay, so the carbon-carbon triple bond of ethine, the triple bonded carbon, is shorter than the double bond, which is shorter than the single bond. Okay, so let's think about this. Okay, when we have our bond length here, we have our sigma bond, which is the one in the middle, and then we have a pi bond and a pi bond. So not only do we have a sigma bond, which is sp hybridized, it is more s-like, so it is going to be shorter. And then you have a p and another p on top of it. So you have 3 bonds pulling those 2 carbons together, and that makes the bond length about 120 degrees. Okay. I'm sorry, the bond length 121.2 angstroms. Sorry. So that's going to be 0.12 nanometers. Okay, but when we go to the thing that only has a double bond, we have our sp2 sigma bond and then our p bond here. So we have a slightly more p-like, so a little bit bigger, and we only have one other p holding it together. When we do that, the bond gets a little bit longer at 1.34 angstroms. So it's increased by 0.14 angstroms. And then if we go with no double bonds and we go with our sp3, that means we have more p character. That's going to be our longest bond possible, and there's no second bond. There's no pi bond. So that means they're going to be the longest bond at 1.5 angstroms. So the hybridization changes bond length, and the number of bonds changes bond length. Okay. All right. So questions on hybridization. We're going to use hybridization a lot. Now, one thing I'm going to show you in the next part is that hybridization leads to molecular shape. Molecular shape tells you what hybridization is. So if the molecular shape changes, the hybridization has changed. If the molecular shape is one way, it's probably a certain hybridization. If the molecular structure is a different way, it's a different hybridization. Was that a question? Okay. So we're going to learn to use molecular geometry and the idea that electrons repulse each other to figure out how what the geometry of different molecules are like. And from their geometry, we can see the hybridization. Well, if we only know the hybridization, we should be able to see the geometry. Okay, so the idea is that electrons are negatively charged. Electrons repulse each other. So that means that the electrons want to be as far apart from each other as possible. And so they're going to spread out in space, but they're also going to repel other groups that are covalently bonded to the atoms. So imagine we're trying to put a whole bunch of balloons into a car and we're trying to shove them all in there. They're going to try to spread out as far as possible. And so that's what we're looking for, what kind of shapes they do when they spread out as far as possible. Okay, so we only have to consider the valence electrons. Remember, the core electrons are done. We don't do anything with them. We're only talking about the valence electrons. And we need to know whether they're shared as covalent bonds, or if they're bonding pairs, which are the bonding pairs, or they're unshared, and their non-bonding pairs are what we call lone pairs. Lone pairs are a little bit different than bonding pairs, but they each take up a certain amount of volume. So we need to know which is which. The next thing we need to know is that electron pairs repel each other. And so that makes them want to stay as far apart as possible. And that generalization means that we can figure out exactly the shape of the molecule by figuring out how many things we have that are spreading each other apart. Okay, and therefore we arrive at the geometry of the molecule by considering both the lone pairs and the bonding pairs. So the non-bonding and the bonding electrons tell us which geometry we have, because those bonding ones are going to tell us which atom is nearby and whether it's a big atom or a small atom. Those non-bonding electrons are also taking up space, so they count toward the molecular shape. Okay, so if we just have two areas of electron density, let's say we had something like beryllium, it only had 2 electrons, it has 2 areas of electron, it's going to give us a linear shape right here, because it can only bond 2 times. Sorry, it'll give us a linear shape. Okay. Now, if we have 3 equal orbitals, we're going to, or 3 equal areas of electron density, like boron, we're going to be flat, trigonal planar, like this. Okay, kind of like that middle part when we had the Sp2 hybridized, where the one was coming up and down. But what if we have 4 equal orbitals? 4 equal orbitals are going to spread each other out as far as possible and give us that 109 degrees. Okay, but if you have 4 things bonded to it, it's going to give you that tetrahedral shape. But what if you have a lone pair? The lone pair still takes up space, which means it forces the 3 things that are bonded to it down. And that gives us what we call trigonal pyramidal. So it's like a pyramid with 3 sides, trigonal pyramidal. Then we can think of things like ammonia are like this, and this is like methane. But what if we only bond twice, but we still have those 4 equal zones? Then we have something like water. Water's bent. Those 2 orbitals with the lone pairs in it take up space and therefore change the molecular geometry. So we have electronic zones and molecular geometry. 4 electronic zones can give us a tetrahedral molecular geometry with no lone pairs, trigonal pyramidal with 1 lone pair, and bent with 2 lone pairs. And then we can actually get very complex out of this. It can go up to 5 and 6 and 7 different zones, but we're going to stick with just these because we can tell most of what we're going to do with organic chemistry in this. So let's look at methane. We have a total of 4 sigma bonds, 1, 2, 3, 4 to hydrogen. And because they're equal in size, all the hydrogens are equal in size, that means that they're going to repulse each other equally all the way around. And when they do that, we get a perfect 109.5 degrees between all the different hydrogens. Okay, so this has 4 equal bonds with 4 equal sized atoms, all repulsing each other with their electron repulsion. So If we take that and change it out from carbon to nitrogen, nitrogen has 5 valence electrons, and therefore it wants to bond 3 times and have a lone pair. So what we see here is it has our Sp2 hybridized structure. It has a tetrahedral arrangement of electrons, but if we look at just the bonds, this is a sigma bond, this is a sigma bond, and this is a sigma bond, it turns out that that lone pair is spreading those out, pushing those down, and these are 107 degrees apart right here. And this big lone pair up here is taking up more space than a bond because it's pushing them from 109.5 to 107. Okay, so those 2 electrons are taking up more space than a sigma bond. Okay, and likewise, if we switched out nitrogen for oxygen, we actually have, again, Sp2 hybridized orbitals. We have 4 orbitals that are equal. Okay, and one of the Sp first orbital is going to bond to the hydrogen, this hydrogen here, and then this hydrogen here. But those 2 lone pairs also take up space. Now notice if they were perfectly equal in size and electron repulsion, they'd be at 109.5. But these push away a little bit more, and therefore the hydrogens in water are only 105 degrees apart, and our molecular structure is bent. Okay. So do we see the difference between electronic zones, which is the orbitals, okay, and the molecular structure, which is the bonded atoms? Those are the big differences between them. Molecular structure is where the atoms are bonded. Electronic zones are where the hybridization is. Okay, in this case, all carbon, nitrogen, and oxygen are all Sp2 hybridized in these structures. Okay, we got 2 minutes left. So I'm going to stop here and we're going to finish up with the other shapes like boron, etc. And then we're going to start chapter 2, which is nomenclature, on on next Monday, sorry. Please go and take the quiz before 11 p.m. tonight on Canvas. If you are having trouble, go ahead and email me. I do have a class at 2 to 3:30, so it might, I'm going to be dark during that time, but other than that, I should be able to try to fix your problems. Again, with this Proctorio, it's best to just close your application, open it up, and just open Canvas, and that should solve most of your problems. But if you have any problems, please email me. I want to make sure you take the quiz today. Okay, take the test quiz for fun, but then you also need to take the actual quiz today by 11 p.m. tonight. All right, questions, comments, concerns? Let's see, 105 of 108. Oh, I only have 3 things to go. Oh well, we were done. All right, I'm going to go ahead and stop sharing and stop recording.